So in this video, what I'd like you to do is show by substitution that this relation between these two integrals hold. They're both definite integrals. One is from 1 to x to the power of n of 1 over t with respect to t, and the other is n times the integral from 1 to x of 1 over t dt. So making an appropriate substitution, show that one would be equal to the other. And the question I'd like you to also explain is, why would you expect this to be true? So have a go. Detailed solution and comments follow after you've had a go at it. So see you in a minute. Okay, welcome back. Let's look at the answer. So what I'd like to do is to show this relation, and I'm actually going to start by asking ourselves why we would expect this to be true. So this integral and this integral really is the same, but they've got different upper limits. They've both got lower limit 1. So let's just look at it for some arbitrary upper limit that I'm choosing to call a. So this integral, the integral of 1 over t with respect to t, is the logarithm of the modulus of t, and we evaluate it at the upper limit and at the lower limit. So from the upper limit we get the logarithm of the modulus of a, and then we subtract this evaluated at 1, and so we get the logarithm of the modulus of 1, or the logarithm of 1. But the logarithm of 1 is 0. So therefore, this integral is the logarithm of a. And note, by the way, because this is going to be useful to us, so note that the integral does not depend on t, and we say that t is a dummy variable. In other words, you could have this integral here, say, you could replace t by something else. Let's say that you were to replace it by L. So you'd have the integral from 1 to a of 1 over L with respect to L, and you would also get logarithm of a. It does not depend on what variable you use here. You just shouldn't be using a if you're integrating with respect to the variable. Okay, so what this tells us is that the left-hand side of our identity is going to be equal to the logarithm of x to the n. So our identity, the one that we want to show, so this is the logarithm of our upper limit, x to the n. So it's the logarithm of the modulus of x to the n. And the right-hand side is n times the integral, and this is exactly the same as that again, but with a replaced by x. So it's n log mod x, and that is a standard logarithmic identity. So what we're seeing here is this identity tells us that the logarithm of a is the integral from 1 to a of 1 over t with respect to t. And this is a way that you can define the natural logarithm in terms of an integral. And if this is true, which it is, it must be the case that all the rules for logarithms follow from the rules of integration. So this identity that we're going to show on the next slide corresponds to this rule for logarithms. So let's have a look at that on the next slide. So in this slide, I want to show this relation. And you will notice that here I have changed the name of the dummy variable from t to u. And the reason I've done this is because I'm going to say, well, t is some function of u, and obviously if I was to also call this t, I'd have something very confusing, like, well, we're going to redefine t as t squared, and that would be a mess. So we're going to give it a different name here, but it's a dummy variable. This does not depend upon u in the same way that this does not depend upon t. So if we look at this integral, t ranges from 1 at the lower limit to x to the n at the upper limit. The other side of the identity we're trying to show, u ranges from 1 to x at the upper limit. So I think it's natural to try the substitution that t is equal to u raised to the power of n. And if we take the nth root of both sides, u, which is the nth root of u to the n, is t to the 1 over n. So it's the nth root of t. And that's the substitution we're going to try. The nth root of 1 is still going to be 1. The nth root of x to the n will be x. So the limits will work. Remember the substitution formula. So we have some function of our variable that we're integrating with respect to, and if there's a factor of du dt, of this function with respect to t, then we can just rewrite this integral as f of u integrated with respect to u, and if it's an indefinite integral at the end, you can replace u by u of t, and if it's a definite integral, as it will be here, we can just change the limits as appropriate. So we're going to need du dt. Du dt, the derivative of this with respect to t, we're going to bring a 1 over n in front, and we're going to reduce the power by 1. So we have t to the 1 over n minus 1. And I think it's less confusing now if we break this into two factors multiplying each other. So there's the 1 over n outside, there's a t to the 1 over n, so that's in the numerator, and then that's multiplied by t to the minus 1, and t to the minus 1 means t is in the denominator, t to the 1. So if we now look at du dt, which we've calculated, do we see this in the original integral? And we don't see all of it, but we do see a 1 over t factor. So that part of du dt is already there. But we don't have a 1 over n and a t to the 1 over n. So let's insert them by hand by inserting a factor of 1. So the 1 over t we're going to leave there, and then we're going to take this and multiply it by its reciprocal. So that means we're just inserting a factor of 1. So our integral is going to be, now, the 1 over t that is initially there has been used as part of the du dt. We need a 1 over n times t to the 1 over n. So to make sure, because they weren't already there, that we're not introducing them by hand, we'll multiply by the reciprocal. So we multiply by an n that would cancel that, and we divide by a t to the 1 over n that would cancel that. So this combination here, if you just multiply it out, is 1 over t, the original integral. So this is completely correct. We've done nothing wrong. So now we can make our change of variables in line with our standard substitution equation. This is going to be the function that we're integrating. The question, of course, is can we rewrite this nicely in terms of u? And the answer is yes, we can. U is t to the 1 over n, so 1 over t to the 1 over n is 1 over u. And then du dt integrated with respect to t just means that we integrate this with respect to u. So n is a constant. We'll pull it out through the integral sign. This is a 1 over u. We're now integrating with respect to u, and this is a definite integral, so the limits here should be for u, and at the bottom, when t was 1, if t is 1, u is 1, and if t is x to the n at the upper limit, you would have x to the n all to the 1 over n, and by the rules for powers, that's just going to be x. So what we see is that our initial integral can, through this substitution, be rewritten in this form, and that is exactly what we were asked to show. So this is one of the relationships of the logarithm function, and we've been able to show it from this approach to the integral. On the next slide, I'll just talk a little bit more about this way of thinking about a logarithm. So on this final slide, I just want to think a little bit more about trying to understand the natural logarithm in this way. So we've said already that this does not depend upon t, the dummy variable, and that it would be exactly the same if we were to choose to write it as, say, the integral from 1 to x of 1 over, let's say, p with respect to p. It's just a dummy variable. But it does depend upon the limit x, and therefore this integral, or this one equivalently, is a function of x. In particular, we see that the logarithm of 1, which is the integral from 1 to x is 1 over t dt, is 0, because our integration range has got 0 width. We're integrating from 1 to 1. There is no width here. So the logarithm of 1 vanishes, and that's something that you would expect. The next thing we might think about is, how do we see that if the variable x is less than 1, so let's say we're looking at the logarithm of a half, say, how do you see that that's negative? Well, let's draw the integrand 1 over t, and we're going to be integrating from from t is 1 to t is x. But that means that we are integrating in this direction. And that means that the horizontal steps in the Riemann sum, because they are going to the left, have negative values. So an integral like this is not equal to this area. It's equal to minus this area. And that's because of the direction of integration. If we were integrating from x to 1, it would be exactly that area. So in this way, you can see that the logarithm of any variable x that is less than 1 and greater than 0, because it's going to diverge as t approaches 0, that logarithm will be negative. You can also understand that as x approaches 0, this is getting rapidly much larger because this is diverging. And that explains the logarithm of x approaching minus infinity as x approaches 0 from above. And then we can also look at the same curve. Y is 1 over t. And if x is greater than 1, then the integral does correspond to this area, and it's above the t-axis, so it's positive. And if x is greater than 1, it gets bigger as x increases, but because the curve is asymptotically approaching the t-axis, what you see is that if you make x a bit bigger, there is another bit to add, so the logarithm increases, but it's not increasing as much as it did here earlier. So the logarithm function increases as x grows, and from this argument and from this argument, you can understand why the logarithm has the following curve. So as x approaches 0, it diverges negatively. It is 0 when x is 1, and then it increases, but the rate of increase is getting smaller and smaller as x increases. And the slope is, of course, 1 over x, because that's the derivative of the natural logarithm. So this way of thinking about defining the natural logarithm does give all of the properties of the natural logarithm. And you could also, if you wish, try to show the other rule for the logarithm that say the logarithm of a times b is the log of a plus the log of b. But I'm going to stop this video here.